organizers for having me out here and giving me the opportunity to give a talk. And obviously we're a bit disappointed with the results of yesterday's football match. And you may not be disappointed here, so I've decided to do something that they like to do in American football, and that's call an audible. I've changed the title of the talk slightly. It's going to be about a lot of the same material, but it'll be a little different. So what's the idea? Unclear. So what's the motivation here exactly, but behind this? So the motivation, at least from my vantage point, goes back a few years to the work of Guillaume, Jones, and Schletenko. So it's the work of GJS from like 08. Yes. Yes. The motivation goes back to work from here, where, and I believe what I believe they were looking for is connections between planar algebras, free probability, and random matrices. Right. That was the motivation. And one of their main results was constructing these diagrammatic algebras, which gave a proof of Poppe's reconstruction theorem. But along the way, I think from my vantage point, the interesting way to study their work, it boils down to studying semicircular elements on graphs. That was at least from my vantage point, I think the key to studying what was going on. So it really boils down to studying semicircular elements, or operator-valued semicircular elements. And so that's kind of bringing me to the motivation of this project, which is sort of, how much further can you carry the study? What other things can be done, et cetera, et cetera. All right, so I'm going to give you the ingredients of what we're going to study, talk about some results I've done in the past, and then move to this laws of loops, whatever that means. All right. So here are the ingredients. So I'm going to start with something I think fairly easy to understand. I'm going to start with a graph, a weighted graph. Again, as a weighted graph. So to take here a weighted graph, the vertex set and an undirected edge set. And I'm going to have this map mu. It's going to be a weighting on the vertices. So to me, it's going to measure some sort of relative size of these things. And we're going to see how to kind of associate canonically sort of semicircular elements to such a thing. All right. So what we're going to do is we form the directed version. And the easiest way to define the directed version is to draw a couple of pictures. So that's what I will do. probably too low if I will do that. So let me just, I'll pull a board right here just so everybody can see it. So if this is a picture here in gamma, this is, say, kind of localized. We've zoomed in. Here's two vertices. Here's an edge. This is something in gamma. The picture that we're going to have in the oriented version is we're just going to double this edge and have it go two ways, as such. So that's the picture in the directed version. And so that's if the two vertices are different. And if there's nothing wrong here with self-loops. Of course, in subfactory theory, these graphs will always be bipartite and these won't exist. But there's, in principle, nothing wrong with having them around. So this is my picture in gamma, some edge. And in the directed guy, well, a loop really only has one direction. So it's going to stay that way. And as we're going forward, it would be smart to adopt a convention here. So I'm going to use Roman letters for undirected edges and Greek letters for ones which are directed. And usually is going to be E and epsilon specifically. So sorry, epsilon is not a quantity that's going to 0, but it's just an edge as such. And you can see here, I have an edge, and it's sort of its opposite edge by just reversing orientations. All right. Oh, hopefully we can understand this. What are we going to do here? Once I've got the graph, I have to kind of produce an algebra. I have to produce kind of a Hilbert module or Hilbert space where this can act. So it's a very natural way you can make this Hilbert space. You take, just for simplicity, let's assume the graph is finite. So we're going to form just the formal complex linear span of the edges. And we're going to put a C naught of V by module structure. So the functions on the vertices will act on the left and right. In sort of the obvious way, well, what would the obvious way be? Well, if I write an edge here, the idea is there's a source of the edge and there's a target of the edge. And when you're looking at it, I like to read things source to target. So the stuff supported on the target can act here. The stuff supported on the source can act here. In other words, this edge will be equal to the following. This thing, where, just to be clear, when I write something, P of some vertex is just the indicator function at that vertex. So the projection. Of course, once one has, so we have this, we need to now put a Hilbert module structure on it. So we have a C naught of V inner product given by, well, I hand you two edges. And it detects if they're the same. And if they are the same, then I get the projection onto the target. And yes, I do want the target. This is the one I want. Right. So once I have a Hilbert module, I have the edges, we do what any free probabilist would want to do, and we form a Fock space. That is it. Yep. So far, the weight has not come into play. It will. It will. The very end here. That's correct. The weight has not come into play. So they form this Fock space by just taking C naught of V, direct sum with the span. We should give the span a name. Let's call it X. Tensor n times over C naught of V. So, of course, this is the standard Hilbert module tensor product. This is a Hilbert module. And, of course, as a sanity check, if I'm in one of these, if I have a string of edges in one of these tensor powers, it is non-zero if and only if it is actually a path. So it's really just kind of a space of paths. This is all this is. Okay. And of course, once we have a Fock space, the next natural thing we have are creation and annihilation operators. So given an edge, you can get this operator, left creation operator. And it's given by, but I think I can write it here, LE of some path, N is you just tack the guy on the front. All right, and then there's the annihilation operator. And of course, these guys, they act on the left. They are bounded. They're adjoinable. All that good stuff. Is there a question? Oh, okay. All right. Okay. So the weighting still hasn't come in. It will now. So we have kind of these operators to work with, and now to get something which has a chance of being tracial, we do something Wojciechowski would do, which is we write down the semicircular elements. Or I guess what I'm about to write down are circular elements. But, yeah. So the weight has not shown up yet. It is about to. That is correct. All right. So now we enter the weight. There we go. All right. How's this going to work? So for each edge, you define XE to be the following gadget. Square root of mu the source, the fourth root of mu of the source of the edge, over mu of the target of the edge, times the creation of the edge, plus the fourth root of the reverse ratio. Times the annihilation, the opposite guy. There's where these come in. So this free graph algebra we're going to examine now we have this. We are just going to take the algebra generated by our scalars and these operators. Now remember, everything here is operator valued, so our scalars just play the role of the functions on the graph. So I'll call this S of gamma mu. And it is, say, the C star algebra generated by C naught of V and the X's. All right. Now, before I talk about some additional properties of this, I'm I want to kind of make two observations that are fairly easy, but I think are pretty important describing this thing. So the first one is this. First thing, I take xe and I take the adjoint. Under this definition, I get nothing other than xe op. And of course, as I'm saying under this definition, I realize you probably can't even see it. There it is. So yeah, if you take the adjoint of this thing, you get exactly what would be considered xe op, because e and e op switch. The second observation is these guys, sort of, but by how I've constructed these operators, this is true. If I compress by the source, xe, then I put the target, this is just xe. So these all kind of live on these various corners. All right. All right. All right, well, this is a von Neumann Algebras conference, so I should probably say something about that. So, question is, what does a von Neumann algebra look like? Well, technically speaking, I haven't even given you a Hilbert space yet, so I have to throw a trace on here, and then we'll get the Hilbert space, the von Neumann algebra, all that good stuff. And the weighting is going to influence the trace. So note, we have an expectation. We have an expectation here from this C-star algebra onto the C naught of V. And it's given by the following. If we set vector 1 hat to just be the sum of all the p's for V and V, then you just take x and you map it to 1, x against 1. Hilbert modular inner products always are linear on this variable. So remember, this is the inner product on the Fock space. This is going to give me something in C naught of V. Well, it's this, no, it's the sum of the P, no, the PVs are, right? Because the vacuum. What? It's a finite graph, so yeah, yes. Yeah, or it's, you could take them, yeah. Otherwise, Dima, you would, if the graph were infinite, you would put PV in both slots and you'd sum it, and this sum does converge in norm. Because everything is finitely, norm limits of stuff that's finitely supported. So that's what you would do, but I wanted to be shorthand about it. Yeah. Okay. The point is, so we have this, and so what one can do now, this is my expectation. This is my E of x. So you can actually get a trace by doing the following. Take the trace of x. Well, we first compute the expectation. So we do this operator valued inner product. This lands me in C naught of V. There's a weighting on the vertices. So I just take the inherent weighting I get. So integration against that measure. Now, this choice of weighting does make this a trace. Sort of only this choice of weighting really does. No, oh yeah, so that's the nice thing, any weighting. It does not have to be for Frobenius per own eigenvector. This is always a trace. I mean, these coefficients, of course, Dima, are dependent on the weighting, right? Yeah. Okay. All right, so that's what we have. All right, now I will state some theorems. And then talk about what I was planning on. All right, so in the context that my graph is the principal graph of a subfactor. Guione, Jones, and Schlatenko study this, and were able to determine that these things are free group factors. So if you change up the weighting, they still are with a catch. So, okay, so first theorem is this. We're going to set, given two vertices, we set NVW is the number of edges in E, so the unoriented edges connecting V and W. So with V and W as endpoints. So the theorem is this. So you take the GNS representation with respect to the trace. So I'm going to take the von Neumann algebra. This is a factor if and only if for all vertices we have the following weighting condition. The weight at my vertex is dominated by the weights of the neighbors. In other words, kind of all the information from the surrounding vertices is kind of enough to cover the projection on the vertex there. Yeah, we're getting there. What? Yes, it's yeah. Yeah, subharmonicity. In this case, you can say a bit more actually. This will be an interpolated free group factor, and there's a way using Dykeham as free dimension to compute the parameter, assuming, of course, that they're all different. So that's the first thing I'll say. And Dave asked me a question about the C-star algebra, so I will address that as well. So the C-star algebra is simple with unique trace if and only if very similar condition, except this goes away. Turns out if you have equality, you can have these non-unital ideals that are floating around here, much similar to the calculations Ken was doing for similar reduced free products. All right. Moreover, we actually kind of know some of the non-commutative topology of this. And so this next thing I will say is joint with Penneys. So following the work of Pimsner, primarily Pimsner, and Emmanuel Germain, we have the inclusion of the vertices. And this inclusion is a KK equivalence. So to be clear, the Pimsner part is actually, these creation operators form a Toeplitz algebra. And it's a well-known result of Pimsner that inclusion is a KK equivalence. But his homotopy actually dropped down. Germain observed this homotopy drop down and covered this case as well. So it's kind of cool. No matter what the weighting is, they all have the same K theory. But the positive cone depends greatly on what the weighting is. So these things are generally not isomorphic, the C-star algebras. The positive cone depends on weighting. is. It is, yeah, K-theory is very trivial. Yes, it is. Yeah, it was actually, you know, when Dave and I were, you know, our initial motivation was examining the GJS C-star algebras, and we really kind of wanted some interest in K1 and things like that, and don't have it. But notice there is sort of this, for those who've studied just the C-star algebra on a semicircular system, this is sort of an analogy to that. And in fact, for a semicircular system, here's kind of the passing note I'll say on this. It's cool being tall, by the way. You can get up here. So if I draw this picture. Yeah, exactly. So if I kind of draw a rose with end petals, this really, you know, on the C-star algebra level, is just the C-star algebra of a free semicircular family. Or on the von Neumann algebra level, it's L of Fn. What the picture is. All right, so how much time do I have left? OK, just enough time just to sort of state the new result I wanted to and probably not get too much into the details. All right, so this was all work a couple of years back. So more recently, starting with work of Dima and Paul Skafranis, there's, and probably actually, well, really back before that, there was sort of, there's been a study into regularity of certain non-commuting polynomials in free variables. So sort of state a few things that have been stated, and then I'll tell you the result I have. So, some previous work. So this is work. So and this is work due to Shlatenko, Skafranis, Charlesworth, Skafranis, Maispeicher, Weber. So the scalar setting, you're going to let x1 through xn be self-adjoint and say finite Fisher information. In fact, actually, it's been relaxed to free entropy dimension, if I'm mistaken. So finite free entropy dimension. Yes. Then, the kind of remarkable result is if one takes a polynomial that's self-adjoint, and it's a polynomial in these variables, then this guy has no atoms in its spectral measure. Non-constant polynomial. All right. So here, of course, well, if I want to look at polynomials of these semicircular, of these, you know, generators on edges, well, clearly the statement is false because all of these guys are just supported under corners by algebra. However, there is a version of this statement that is true, and I will write that down, and I'll be done. So let P, this be in a complex algebra generated by the projections and these x's. We're going to assume, we're going to let V be of minimal weight. P self-adjoint and supported under this projection. So i.e., this P is just going to be a linear combination of some loops. Then the law of P with respect to trace PV dot in PV S gamma mu. PV has no atoms. Yeah. So I'm on a roll today. All right. You know, every time I write this theorem down, there's always like one thing I forget. Today, that's the thing I'm forgetting. Yeah. But anyway, this holds. The sort of silly remark is this is kind of the only version that can possibly hold. Because if you're sort of a loop supported at a bigger vertex, if you get vectored through a smaller one, there's a trace lying around. You're clearly going to have a kernel. So this is the version to expect here. Anyway, I'm very sorry for going a minute over. I hope you forgive me. And enjoy our coffee. Thanks for listening.